totally clear. At least this is what I understood from the few questions. And then, of course, we will look at some exercises or some other. Today, I will publish on InfoStud the dates for the exam. Please refrain from trying the exam just to see how it is. If you decide to do the exam, you should be 100% sure that you are up to the exam, okay? I will come back on this before the last class. So first, any questions? Okay. So on Friday, we discussed this concept of observability. And in particular, we discussed, I tried to give a physical interpretation of this property so that everything would be more interesting, or at least more comprehensible. But I realized that maybe there are still some aspects which are not clear. So let me go back on this concept of observability. And in particular, one of the critical examples were when we had two systems in parallel, for example, x dot 1 equal minus x1 plus 2u1. Since they share the same input, we can write u. And the second input, the second system, x2 dot equal minus x2 plus u, and the two systems would add up at the output, giving y. So this is an interconnected system for which we know that there is a loss of observability and controllability. This is what we studied when we introduced the natural modes, controllable and observable. Now, of course, we have a new tool. So let's rewrite the interconnected system. We know we can choose as state x1 and x2, so that when we compute x dot, that would be the derivative of each component, we would have minus 1, 0, 0, minus 1, x1, x2, plus 2, 1, u. And I mean, in this parallel interconnection, we would have 1, 1, so x1 plus x2 times x1, x2. And when we compute the observability matrix, CCA, okay, we would obtain 1, 1, this is C, and then minus 1, minus 1. Clearly single. Then we said, okay, let's do a slightly more general, so it's not really a parallel system with this choice of the output. So let's take a generic output. So we have the two systems like this, and we could ask ourselves, is there any choice of the output for which the system does not have a non-observable subsystem? So so this is the question we may ask ourselves. Well, let's compute the corresponding observability matrix. We have C1, C2, and we have minus C1 and minus C2, which we see that it is still singular. So here we note a difference with respect to the physical example I was mentioning during the last lecture. When I was taking as physical system flexible beam, and I said, depending on where the sensor is placed, which means depending on the output we choose, we may have that some natural modes are unobservable or not. So there was something changing when we were changing sensor. Here in this particular configuration, and in particular, of course, with this A matrix, the B matrix has no effect when we talk about observability. We see that it's something even more general in this example because it is independent. The loss of observability is for any choice of the output. So it's something even more structural with respect to before. Okay, then I try to make things a little bit more clear by saying, okay, what does unobservable mean? And I said unobservable is equivalent to undistinguishable, I think, from zero, from the origin. What do I mean by this? Let's imagine we have an initial state, XA, and zero as initial state. Okay, so we can see things in a general way. If we apply an input U of t, the same for both situations, if the corresponding output evolution coincide, then we would say that this initial state is indistinguishable with respect to the zero initial state, because applying the same input, they produce the same output. Well, if we write these full output evolutions, we would have y1 of t, c e to the at xa plus c e to the at minus tau b u of tau and d tau. We assume d is equal to 0 just to make things. The second output corresponding to the zero initial condition, of course, would have this first term equal to 0, and then we would have the forcing term coincident. So we understand also that in this analysis, we can also not consider this, because when we make the difference to see if there is any difference in the output evolution, y1 minus y2, for example, these two terms, since they are coincident, we are doing this reasoning for the same input, is telling us that we are going to say that XA is indistinguishable from the origin, if and only if C e to the AT XA gives the same free output evolution, which for 0 is equal to 0. And if this is true for any t greater than 0. Okay, so, well, this is equivalent to saying that XA belongs to the kernel of C e to the AT for every instant t greater than 0. So if I make two experiments, no forcing term, and I have two initial conditions, one is 0. If I have an initial condition 0, there will be no evolution since there's no input. If I take another input and it creates no free evolution, this state is going to be unobservable. Okay, so this is equivalent to say that the state XA is unobservable. Okay, so now the concept of unobservable state is hopefully a little bit more clear, but how can we say if a state XA is unobservable or not? Okay, since this is really not part, let's say, of the program, so I'm adding this information just to hopefully make everything clear. XA is, well, this is something we already know because we said, sorry, this is clear. We said that the state is unobservable if it belongs to the kernel of the observability matrix. Okay. So we have a way to find all the unobservable states. So all those states which would create free evolution identically equal to 0 for any t. Now, let's assume that S is observable, the whole system, or the whole state space. Okay, this is, of course, equivalent to saying that the kernel of the observability matrix is just the 0 vector. Okay, so last time, Friday, I said if the system is observable, it means that we can reconstruct the state where we started from. And that was, I understand, not very, very clear how we would achieve this. Well, in fact, the things are not so complicated. So let's assume that U of t is identically 0. Of course, this result can be also extended easily when the case, in the case where we have an input. And let's assume that we are starting from an initial condition, which is unknown. But we can measure the output y of t. So the question we were asking is, can we reconstruct x0 where we started from just by the knowledge of the system matrices? I'm just considering the case, I would show just the case for d equals 0 and the output. From this knowledge, is it possible to reconstruct the initial state where we started from? So when u equal to 0, we have this simple relationship here. And we cannot take the inverse, because if we have, for example, Caesar system, C is a row vector, e to the at is a square matrix, so the product is a row vector, and we cannot just take the inverse. We could take the other kind of inverses, but that's different. What we can do is rewrite this in the following way. So we could, let's say, pre-multiply by this strange matrix, which is E to the A transpose T C transpose on both sides. So this would lead to E A transpose T C transpose Y of T equal E A transpose T C transpose C A transpose T x0. And then we could integrate from 0 to T bar what happens is that x0 is constant. Okay, so we can take out x0 from this matrix. And what remains here is something that we can write as 0 T bar EA transpose T C transpose C EA transpose T in dt times x0. Now this is a very special matrix which is called either Gramian or sometimes with double N. It's not, you can find both of them, and in particular this is the observability Gramian. And the result...
Posso fare una domanda?
Prego.
Nell'integrale entrambe le matrici A sono trasposte?
Ah, no, sorry. Sorry. When we multiply here, this is... Okay, thank you. So what comes out is that if S is observable, then this GO of T bar is equivalent to saying that this matrix GO of T bar is non-singular for any T bar greater than 0. So what we have here is we have a first integral which depends on the output. We have a Gaussian matrix and the initial condition, and this Gaussian matrix is invertible. So you see that we could rewrite this as times this integral here. Okay, so this is the way one could compute from the knowledge of the output from 0 to t bar, the initial condition where the system started from. Okay. Now, what's a little bit more interesting is what happens. Well, before we do this, there's of course a dual result when the system S is controllable.
Professore, mi scusi.
Prego.
Ma la matrice di Gramian non è tutto l'integrale?
Questo integrale qui.
È tutto quello, è tutto quanto, giusto?
Questo qui.
E allora perché nell'inversione ci rimane l'integrale con le trasposte?
Questo pezzo qui?
Esatto. Ah, ok. Sì, giusto, mi scusi, non avevo considerato quello.
Sì.
Grazie mille.
So the other result is a dual. I'm not going in any. Avanti. Lezione. Ho dimenticato di mettere l'avviso, scusa. Aspetta che... Sì. Sorry, I forgot to put the... So if S is controllable, there is, of course, a controllability Gramian. And it is possible to find explicitly in the same way, I mean, in a very similar way, the input that drives the initial state from x0 to xa in t seconds. So these are dual results. So I would like to make clear that this is not subject to any exam question, okay? It's just to really try at least to make these things clear. So I was saying, what happens if the system S is not fully observable, okay? Well, it means that we have a non-zero or null space of the observability matrix. So let's take two states. Let's take XA belonging to the kernel of the observability matrix and XB not belonging, okay? So let's call YB. The free evolution from the initial state XP. So we have C e to the AT XP. We are not considering the forced evolution because in terms of observability, it doesn't add any further doesn't have any importance. Of course, we could have a forcing term, but everything would remain unchanged. Now, let's see what happens if we take as an initial state, state xb plus any constant alpha xa. So we would have y of t equals c e to the at xb plus alpha xa. But since xa belongs to the kernel of the observability matrix, we would have c e to the atxb plus alpha c atxa. And we saw that any unobservable state is such that this is identically 0 for any t. So we are saying that any initial state that is composed by an observable state plus an unobservable state or a linear combination of unobservable states would give exactly the same contribution in the free evolution. Let's make this even more clear through the previous example. So these are the matrices. So if we go back to the example, the observability matrix. So C was 1, 1 in the first case, and CA -1, -1. So the kernel of this matrix, the null space, is generated by the vector 1, -1. X1, X2, this is the whole state space. We can graphically represent the null space or the, okay. So this is, so this is a set of unobservable states, and you see it's a linear subspace. It goes through the origin always. This is why we are considering the unobservable states, because these are kernel, and so they are linear subspace. The observable states are not a linear subspace. Well, if we choose an initial condition like XB here, this would, for example, be okay with these coordinates. We're saying that XB plus any vector, so any parallel, would produce the same state evolution. Oops. So any other initial state here produces the same state evolution as that XB. Okay, hopefully this is starting to make some, let's say, sense, or at least analytically, but the last time one of you asked, we saw an example, a physical example, the mass with friction, And then we said, this is totally different if we have some, let's say, elasticity. Let's see if knowing what we have seen up to now makes everything more clear. So let's take the mass and friction system. So mx double dot plus kx dot equal F. And we said, if we take as output the velocity, we have clearly an unobservable subsystem, etc., etc. So now let's interpret these unobservable states as the states that are unobservable in the sense undistinguishable from the origin. Okay, let's see if this makes sense. So A matrix, when we get back into the state space representation, is 0, 1, 0, minus, sorry, this is, let's not use K. Let's choose mu to be consistent with the usual notation. Okay, and we said if we choose the velocity as output, we would have 0, 1. So that the observability matrix becomes 0, 1, and 0 minus mu over n. So the kernel is clearly generated by any vector parallel to 1, 0. If I multiply this observability matrix times alpha 0, I would always obtain the 0 vector. In these coordinates, this means whatever initial position, first component, with 0 initial velocity, this is the set of unobservable states. Well, if I initialize my state in any initial position, 0 initial velocity, clearly the output, which is the velocity, is identically equal to 0 when there is no input. That's, I hope, even more than obvious. And this reasoning here, the set of all, if I start second, let's say, part of this reasoning, let's choose XB not belonging to the kernel of the observability matrix. For example, let's start with 0 initial position and a given initial velocity, of course, non-zero. Well, this gives as output velocity c e to the at v0. But if I start from this initial condition, from any initial position, this is belonging to the kernel of the observability matrix, then the resulting output, the velocity in this example, is going to be, again, c e to the at v0, since all the second term will give a 0 contribution. Okay, so now at least this example of mass friction is hopefully clear. Then the last question was, but why the mass spring damper is different? Well, there are many. So when we study the mass spring damper system and we choose, of course, again, the velocity as output, so x dot. So we are in the same situation as before. Why? What's the physical reason that makes the system observable? Well, there are many possible ways of looking at this. The first one is saying there are no initial conditions different from the zero initial condition such that the velocity is identically zero for all t. And this is obvious because if I have an initial position p0, even if I start from a initial velocity, this initial position due to the term kx would generate a force, and therefore it generates a movement, etc., etc. So more details than this, I think it's quite difficult. So I don't know if the student who had these doubts on Friday now is present and if everything is more clear or not.
Professore, io le avevo fatto una domanda sullo mass spring damper, per me è molto chiaro, non so se si riferiva anche a qualcun altro.
Non mi ricordo ovviamente chi fosse, ma ok, bene. Perfetto. Okay, so now let's proceed a little bit more, let's say, oriented to questions. So there's one aspect which typically leads to some errors, and it's the following. So if we take controllability, and you can make exactly the same reasoning for the observability. And we have a system S which has a dynamic matrix in this form. Where, of course, this partitioning is consistent, okay? So A11 is a square matrix, A22 is a square matrix, and all the other matrices. So what can we say when we see a structure like this? Of course, we could represent again in a block, let's say the two subsystems, and we would again see something like this. So we could, of course, compute the controllability matrix. And all these would, at least initially, say the following. The natural modes of A22 are not controllable. or if you prefer, the system S2 characterized by the matrix A22 is not controllable. And this is true, okay? A typical error is the following. Just imagine you are given these matrices A and B. Having this structure implies that A22 is not controllable, but we cannot say anything about A11. So this does not mean, if we have this structure, that A11, B1 is controllable. And you would say, but how is this possible? We have this Kalman decomposition, etc. True, but if we start from a given A matrix with this structure, nobody is telling us that this is a result of a Kalman decomposition. No, it's just we do not know the history that brought to this A matrix. Let me take an example. Let's take this matrix. -3, 2, -1. No, I think it should be 1. -2, 0, 0. And then we have 1, 1, and -1. And B, 1, 1, 0. Okay, so we look at this matrix, we recognize this block triangular structure for A, and we see that we have the correspondence in B. So when we think about the Kalman decomposition, so this looks really like the result of a Kalman decomposition. So what I'm saying now is that this is for sure uncontrollable. But let's compute. Let's check if A11, B1 is controllable. Okay, so we know that we should compute controllability matrix for A11, B1. So B1 would be 1, 1. Then we would have -3 plus 2, -1, 1 minus 2, -1. And we see that A11, B1 is not controllable. Or if you prefer, if we go back in the original matrices A, B, let's imagine that we do not recognize any special structure. It's okay, let's compute the controllability matrix. Controllability matrix would be, for the full case, B, AB, A square B. This leads to 1, 1, 0. -1, -1, 0. And I think this should be 1, 1, 0. Okay. So what is the rank of this matrix? Rank of P. We see that for sure it's not 3 because of the presence of this 0 row, but we see also that we cannot find any minor of order 2, which is non-singular. The best we can find is a minor of order 1, which is non-singular. So the rank is equal to 1, which means that if we compute the Kalman decomposition, the resulting decomposition would have the structure, sorry. So here we would have a 2 by 2 matrix, here a 1 by 1 matrix. So we would have 0, 0, and some other terms here. A11 would be of dimension 1, and B would be in the new coordinates B1, a scalar, and 0, 0, which is different from what the original system was. Okay, so be careful. It's not automatic, but given this structure, the original structure, we have the A11 B1 block, which is fully controllable. You need to check this. If you get there through the composition, it's guaranteed that the A11 B1 is controllable, but not otherwise. So A11 B1 controllable only if obtained through controllability decomposition. Okay, so this is, since this is a typical error, and I would like to avoid that you get this. What else?
Professore,
Mi dica.
posso farle una domanda su quello che ha fatto prima riguardo all'osservabilità?
Sì, sì.
Volevo chiederle, quando ha fatto vedere che una matrice se era, diciamo, se O era inosservabile, dava dei modi che non erano osservabili, al variare di C rimaneva sempre inosservabile, ma potrebbe essere che al variare di C cambiano i modi inosservabili?
Allora, the question is, we have a system S characterized by a matrix A. So let's see what happens. With different C. So we can have different natural modes become unobservable. This is your question, okay? So by changing the C, I can obtain, not always, but I can have that with one C for the same system, I have one unobservable mode. If I change C, I have another unobservable mode. And you know this, in fact, because when we wrote C e to the at x0, in the case n equal 2, and lambda 1 different from lambda 2, we had, using the expression for the exponential, u1 transpose. Let's take this x0 out. E lambda 1t, C u2, u2. Okay, you remember this expression, hopefully. And we defined initially that this natural mode is observable if C u1 is different from 0. So you understand that with different C vectors, we could make this one different from 0 and this one equal to 0, or this one equal to 0 and this one different from 0, or of course, both different from 0. Okay? The example we saw this morning is things do not change when we change C. Did I answer the question?
L'unica cosa, professore, allora, se cambio C potrebbero cambiare i modi che sono inosservabili.
Sì.
Sì, che sono inosservabili, questo mi è chiaro. Però se diventassero entrambi, osservabili non è possibile.
Perché?
Non abbiamo detto prima che abbiamo fatto vedere
quella struttura lì.
Ah, ok, quello era un caso particolare.
Quello era un caso in cui per ogni C avevo un sottosistema inosservabile. Ok? Ma in generale no.
Ok.
Okay. So you can clear?
Sì.
So we talked about this example, which I think is quite curious. So let's imagine we have this cart, and we have two pendulums, L1, and let's assume that I have M1, M2, length L2, length L1. And let's say that the two angles, we have θ1 and θ2, the two angles with respect to the vertical, okay. And we have a force here. So you could find the nonlinear dynamic equations. And we clearly have that θ1 equals 0 equals θ2, θ1 dot equals 0 equal theta 2 dot, and any position of the card with 0 velocity, these are all equilibrium points, okay? So we can linearize this strange system around, let's say, the vertical position for the pendulums. So we know that the result that we're going to find is going to be local, so valid only for initial conditions which are not very far from the equilibrium point. And then we can, let's say, get rid of the dynamics of the mass m. Okay, we can, and what comes out is something that looks like this. M1 V dot plus L1 theta 1 double dot equal M1 G1 theta 1. You see here the linearization of sin theta, which becomes theta 1. We would have M2 V dot plus L2 theta 2 double dot equal M2, sorry, G theta 2, where V dot is velocity of n, as if this was a new input. So through F, we can command the velocity of the card. And so we take directly that as an input. So we assume that this is the input of our system, which is equivalent in at a certain level of choosing F as the input. So when we have this linear system, we can rewrite by choosing the state Z, theta 1 dot, theta 2 dot. And in these coordinates, we would have Z dot equal AZ plus BU, where U is equal to V dot. Well, if you compute these matrices, you would have an A matrix, which looks like 0, 1, G over L1, 0, 0, 0, and then something like this, 0, 1, G over L2. So you see we have no friction or damping, and B would be 0 minus 1 over L1, 0 minus 1 over L2. Okay, now the question is there a control input U of t such that starting from initial conditions theta 1, theta 2, theta 1 dot, and theta 2 dot different from 0, 0, 0, such that it brings the system to the equilibrium point. Or if you prefer, we start like this even with non-zero initial velocities for the two pendulums. And this input, u of t, will move the card such that we asymptotically have this situation here. So if you remember what we saw previously, when we talked about the controllability Gramian just for a few seconds, we said controllability Gramian allows us to compute the control, the input, which would bring the system from any initial state to any other state. And this is possible if and only if the system, this Gramian matrix is non-singular, which is equivalent to asking that the system is controllable. So we see that it's exactly this kind of formulation that we are having in this problem. So we know that this input exists if and only if the matrix S is controllable. Now we have A, we have B, so we could compute the controllability matrix. So B is 0 minus 1 over L1, 0 minus 1 over L2. A, B would be minus 1 over L1, 0, minus 1 over L2, 0. A square B would lead to G minus G over L1, 0 minus G over L2 square. And finally, A cube B would be a minus G L1 square, 0. Okay, so to see if the system is controllable, we should compute the determinant and see when this determinant is equal to 0. Now, before we give this result, let's try to imagine. First, do you think, it's possible? Imagine we have like these two pendulums that start like this. Can I move? Are you able to move this card such that these two pendulums go back to the vertical position? Any answer? Are you able to do that? Is it possible? No idea?
No, professore, perché se vado verso destra, uno lo addrizzo, mentre l'altro lo sposto sempre più verso sinistra. Quindi non c'è una soluzione, ma probabilmente non c'è una soluzione nemmeno se stanno tutti e due piegati dallo stesso lato. Cioè, forse se hanno la stessa massa e la stessa lunghezza dell'asta, sì, e stanno piegati dello stesso angolo, altrimenti bisogna vedere quali combinazioni.
Okay, so we have a candidate solution, and I'm sorry to say that all your conclusions are wrong, okay? But this is the fun part of it. Aspetti un po' di... Okay. Well, if you compute this determinant, you will find G over L1, L2 square minus G over L1 square L2, which we can factor as Gn1 L2, 1 over L2 minus 1 over L1. And this determinant is different from 0 if and only if L1 is different from L2. So the conclusion is, if the two pendulums have different length, you said equal length, that's why I said totally. There exists an input which brings back the two pendulums in the upright position. It's not evident, you said, if I start like this, if I move this side to make this go like this one will go down further. Yes, but if there are different lengths, you could do a little bit of this and then a little bit of that, so you would, obtain something like this. If you do not trust me, check for the controllability Gramian. And compute the input and do a simulation, okay? So that's why I like this example, because it's absolutely not intuitive.
Io credevo, professore, solo con un singolo impulso da riaddrizzarli tutti e due, allora dicevo, quindi non è mai, quasi mai possibile.
Impulso è una cosa, è un ingresso molto particolare. Qui
nel senso,
l'ingresso lo può scegliere come le pare.
Un unico input in un'unica direzione, diciamo. Quindi o
non le ho vincolato la direzione.
Quindi ho detto subito, no, non è possibile. Okay, sì.
Ma anche se le dico, guardi, l'ingresso può essere così, non è evidente la cosa, no?
No. Certo.
So now we see that this is an existence result. Theoretically, we have that such an input exists, but the result is local, because we are doing this analysis on the linear approximation, okay? And secondly, the result assumes there are no limitations on the control input, V dot. We could, the control that achieves this may require very high force or acceleration, V dot, okay? And maybe your actuator is not able to achieve this. So we should always be extremely careful when we use these controllability and observability tools, because going through the controllability and observability matrix is just telling us it is possible, it is not possible. But the price we should pay for this to be, even if it's possible, it may not be realistic. Okay, for example, I think I have another example. So, very fast example. There's so if you have an airplane, okay, this is stylized. You have a roll and you have pitch. So again, the dynamics of an airplane are rather complicated, etc. You could see just some motions. If you do a linear analysis and you look at here, you have these aileron that could go up and down. So let's consider these as input. And okay, no, we may have also so we can represent very roughly the dynamics like this. So XPXR. So this is a pitch and this is rho dynamics in a linearized setting, etc. We would have AP0, AR, and some matrix here, epsilon, XPXR, and then we would have, with respect to this input, we would have BP0 delta E. If we have here, let's say, these that can also move. Okay. This could be defined as delta A, these angles. We would have some other 0 B, 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 R delta A. So the question is, we are asking if it is possible to change the pitch with delta E, okay? So what comes out, so if you take delta A equal to 0, you have this B matrix, the A matrix does not change, and you have this epsilon. I'm writing epsilon because this is very small. So if you compute the controllability matrix, you would find that the system is controllable. But since this coupling is extremely small, no airplane is going to ever use these inputs to change the pitch, okay? So this is just to say that be careful when we have a controllability result. This is one step. We also need, in general, in practice, to understand if this is the best choice to obtain that movement or if there are other alternatives. Okay. So let me go back to some exam. For example, we could okay, let's assume we have, so this is an exam exercise, okay? So maybe it's a little bit more direct for you as interest. We have a system described by a state space with matrices A, -1, -2, 2, 0, -1, 0, 1, -1, 0, B, -1, 0, 2, C, 0, 1, 1. And there were two questions. First question, assuming the state measurable, so when you hear state measurable, you understand that we are in a state space setting, because when we deal with transfer functions, etc., we are just looking at the output. Assume the state, build a state feedback. So find a state feedback, if possible, such that the closed loop system is asymptotically stable and with all eigenvalues coinciding. The second question is, show that it is possible to solve the same problem with an output feedback controller. So you do not, in this case, it was written explicitly, you do not need to solve this second problem, but you need to give the structure symbolically of the controller. Okay, so we start, the first question is rather clear. If possible, find the state feedback such that the closed loop system is asymptotically stable. So what we have is, let's compute the two matrices, since we will also need, we may also think about solving the second step through an observer and using the separation principle. So we're going to compute the controllability matrix P and the observability matrix. So -1, 0, 2, 1 plus 4, 5, 0, -1, and then A squared B, I do AB, A times AB. So -5, -2, -7, 0, 5. Let's do the observability matrix. We have, so C, sorry. C is given by 0, 1, 1. Then we have 1, -2, 0, -1, -2 plus 2, 0, and 2. Okay, so let's see what we understand from here. Well, clearly, for sure, this is not a full rank, but we can find a submatrix, a minor order 2, which is non-singular. So the rank of P is equal to 2, strictly less than 3. While if we compute the determinant of the observability matrix, we'd have 0 plus 0 plus 0 minus 2 minus 2, so minus 4. So it's different from 0. Okay, so the system is fully observable. We know that if necessary, we could build a dynamic observer with absolutely no problem. While answering the first question, we should either look at the eigenvalues and find out through the PBH test which one is uncontrollable. There will be just one natural mode or eigenvalue which is uncontrollable, since the rank of P, the loss of rank in the controllability matrix is 1. Or we could compute directly, since it is required to stabilize and find the stabilizing feedback, we could directly find T minus 1. To find T minus 1, we need to find the base of the image of P. We know that such a base could be chosen as the linear independent vectors. For example, the first two. But when we look at these two linearly independent vectors, so they define a plane in R3, we see that any linear combination is characterized by having the second component equal to 0. So if we have X, Y, and Z as a 3 direction, etc., the subspace is characterized by having the second component Y equal to 0. So it can be also generated by a much easier matrix, which is 1, 0, 0, and 0, 0, 1. This step is not necessary, but it's much, it makes computation much easier. And it's going to be clear from the choice of T minus 1, base of the image. Okay, now we have a very simple choice, 1. And clearly, we're going to complete with the simplest one, which is the one that has a component on the second element. You understand that if you had kept the original vectors, you could have found, of course, completion, but then the computation with no help, computer or calculator, etc., would take you much longer. And this is exactly the situation that you will have during the exam. So T should be such that T minus 1T gives the identity matrix. Okay, so we see that if I pick the first column, I would have the first column of the identity matrix. If I pick the last column, I would have the second column of the identity matrix. And if I pick the second column, I would have the second column of the identity matrix. And so we have that T equal T inverse in this very special case. So now it's just a question of computing T minus 1. We know what we are expecting. So we have 1, 0, 0, 0, 0, 1, 0, 1, 0, a matrix. Okay. I have it here. So the A matrix is -1, -2, 2, 0, minus 1, 0. 1 minus 1, 0. And t minus 1. So we have. So this first row will give us the first row, minus 1, 2. The second times A will pick up the third row, so 1, minus 1, 0. And this one will pick up the second, so minus 1, 0. Times T inverse, which is the same. Okay, so this column will pick up the first column of this matrix. So we have minus 1, 1, 0. This will pick up the last one. And this will pick up the second one. B tilde is TB. BB is equal to minus 1, 0, 2. So we have minus 1, 2, 0. Okay, let's check if the computation is correct. The controllable subsystem will have dimension 2, the rank of, okay, we see that we have this block of zeros in the right place, and similarly for the B. By construction, this submatrix A11 and this B1 are controllable. We have the uncontrollable system. Which is characterized by the eigenvalue minus 1. Okay, let's now think we have a clear picture. Can we solve the problem? Can we make the closed loop asymptotically stable with all the eigenvalues coinciding? Well, since the eigenvalue of the uncontrollable subsystem is already asymptotically stable and will not be moved by any state feedback and, of course, any output feedback, the only choice is we can move the eigenvalues of the controllable subsystem in minus 1, minus 1, since the requirement is that all three eigenvalues should coincide. And so how would we do this? Well, we would have a P star, let's say A11 tilde, or let's say P star dimension 2, just let's call it P star, equal lambda plus 1 square so lambda square plus 2 lambda plus 1. So we need to compute this in A11 tilde, where A11 tilde is this matrix here. And so we should compute Okay, this is a computation you can easily do. A11 tilde square plus 2A11 tilde plus the identity 2 by 2 matrix. And this would give a matrix. We need to apply the Ackermann formula, the controllability matrix of A11 tilde B1 tilde. We know this by construction is controllable. So if we find that the resulting controllability 2 by 2 matrix is singular, it means we made a computational error. So we have B 1 tilde equal to minus 1, 2. And A11 tilde B1 tilde is equal to 1 plus 4, 5. And minus 1. This is A11 tilde B1 tilde. This is non-singular. And so from now on, it's all straightforward. We can compute minus 1, take the last row, gamma, tilde. And finally, we would have that F tilde, which assigns the eigenvalues to this controllable subsistence. The desired eigenvalues minus 1 and minus 1 would be minus gamma tilde P star A11 tilde. Once we have this F star, 1, we have F tilde equal F1 tilde 0. And then we should go back in F, usual relationship. And finally, we would write the observer in a generic form. We know it exists since the observability matrix is non-singular. And then we can compute the controller as xi dot equal A minus K6C plus BU plus KY, but BU is FC, and so we would have the controller. This is pure theory. A plus BF minus KC plus the input Y multiplied by K, and the output would be FC. So these are the dynamic equations of the controller. Questions? Okay, it's not much of the...
Prof, scusi, non ho capito, ma quest'ultima parte conclude il secondo punto?
The question was, show that it is possible. Well, it is possible. We say that it is possible after saying that, after seeing that there exists a state feedback which stabilizes, and in this case, the system is observable. Okay. Okay. If the first question had no answer, then the second would not have an answer, of course. We cannot achieve by output feedback what we cannot achieve by state feedback. It's a necessary condition. Ok?
Sì, però cioè, comunque non bisognerebbe utilizzare il principio di separazione.
Questo è il principio. Questo è il principio di separazione. Separation principle. Oops. When I use this, okay, this is separation principle.
Ah, ok, sì, perfetto, sì. Grazie.
Okay, so another easy exercise exam is given a system S, x1 dot equal alpha x1, x2 dot equal minus alpha x1 plus x2 plus 2u, and y equal x1 plus x2. So there were 3 questions which study in terms of alpha parameter belonging to R if system S is stabilizable through state feedback, if there exists an asymptotic observer, and if the system S is stabilizable through output feedback. Well, it's really, so you have A, B, C. I'm not going now. I think we do not have the whole time, but I think it's rather standard. You have the 3 matrices, and in particular, A depends from a parameter alpha. So the first question A is equivalent in studying the controllability as a function of the parameter alpha. So maybe this we can do. We have time for this. So A matrix is given by alpha 0 minus alpha 1. B is equal to 0, 2. Okay. Eigenvalues. So we have an important information. Lambda 1 is equal to alpha and lambda 2 is equal to 1. So stabilizable state feedback. Controllability 0, 2. 0, 2. So the system is not fully controllable. Okay, if you really want to, we can either choose a change of coordinates. So 0, 1, the base of the image, and 1, 0, completion. Or we could, and then let's say, do the separation, or we could do the PBH test. So let's consider first lambda 2 equal 1, A minus lambda 2 identity. B gives alpha minus 1, 0, minus alpha 0, and 0, 2. So we see that if alpha is equal to 1, then we have a situation in which we have two coincident eigenvalues in +1, and we know that the PBH test is telling us if the system is fully controllable, since the PBH test for lambda equal 1 is not verified, and so we have unstable, uncontrollable subsystem. There is no feedback such that it stabilizes the system. If alpha is different from 1, the eigenvalue lambda 2 equal 1 is controllable, since the rank of the PBH test is equal to 2, but this does not imply that the system is stabilizable yet, because we know that if lambda 2 is controllable, we have that the system is not controllable. Since we have only two eigenvalues, one is controllable, means that alpha is not controllable. And therefore, alpha will characterize the uncontrollable subsystem. There exists F which stabilizes the system if and only if alpha is negative. So if the uncontrollable subsystem is already asymptotically stable. So I think this is a rather interesting exercise. You could then check observability, etc., etc. Okay, if needed, if you require, just tell me on Thursday to come back on this exercise, and we will complete it. Tomorrow there is, if anybody makes a request, office hour at 5 o'clock. Questions?
Professore,
Erika.
a me non è chiaro il nesso che c'è tra lo state feedback e l'output state feedback, nel senso che...
No. Output state feedback non esiste.
Scusi, output feedback. Nel senso che mi è chiaro che se il sistema è controllabile e possiamo costruire un asymptotic observer, allora sappiamo anche come costruire il controller per l'output feedback. Non mi sono chiari invece i casi del tipo: il sistema è controllabile, ma i modi non sono osservabili. In quel caso è possibile ottenere un output feedback che stabilizzi il sistema?
So, okay, let's briefly analyze this. Otherwise, I suggest if you can tomorrow, 5 o'clock, you send me first an email. But so your question is, the system S is controllable, but not fully observable. Can we say if there exists or not an output feedback, output stabilizing controller?
Sì,
Okay.
professore.
So this says there exists U equal Fx as if the state was available such that the closed loop system is asymptotically stable. So we should understand this unobservability, what consequences it has. We know that we can build an observer if the system is detectable, which means that since we are assuming there exists an unobservable subsystem, if and only if the unobservable subsystem is asymptotically stable. Okay. If the unobservable subsystem is asymptotically stable, I can build a dynamic system which reconstructs asymptotically my state, and I can use that observer in conjunction with F through the separation principle. If it is not detectable, if the unobservable subsystem is unstable or marginally stable, then we cannot build an observer. Ok?
Ok, professore, molto chiaro. Quindi noi abbiamo abbandonato l'ipotesi che lei ha detto che era troppo richiedere di conoscere lo stato iniziale e di conseguenza necessita...
Sì. Quello era solo per farvi capire, diciamo, se dice sì, ho il modello, conosco l'ingresso, beh, teoricamente conosco tutto, conosco l'evoluzione, no, perché non conosco la condizione iniziale.
Ok, ora è chiarissimo, la ringrazio molto, professore.
Niente, mio lavoro. Ok, altre domande? Se no, sono disponibile domani pomeriggio.
Professore, mi scusi.
Mi dica.
Ok, allora ha detto che domani abbiamo la possibilità di fare un colloquio dalle 5?
Certo.
Ok, no, io le avevo mandato già una mail la settimana scorsa.
Reali?
Comunque,
È lei? Sì, senta.
Sì.
Dunque io non le ho risposto perché ho avuto, diciamo, però
No, chiaramente.
un paio di cose. Quelle foto io le leggo difficilmente.
Ah, ok.
Ok, prima cosa, le avrei infatti risposto questo. Seconda cosa, in uno degli esercizi c'è un chiarissimo errore in un calcolo, mi pare, della funzione di trasferimento, c'è uno 0 che è sbagliato, uno 0 di una funzione di trasferimento, mi pare ora di ricordare. Allora, quando lei fa, diciamo, quando ha questi dubbi, ovviamente, no, faccia tutte le domande, tutto quello che vuole, però nel frattempo, prima che io le risponda, cioè, lei ha degli strumenti tipo MATLAB in cui può studiare, verificare se la funzione di trasferimento che lei ha calcolato è quella giusta, se i diagrammi di Bode sono giusti, se la risposta è quello che è. No? C'ha degli strumenti numerici che sono utilissimi. Intanto, no, si toglie molti dubbi, eccetera. Io sono disponibilissimo, però le consiglio comunque di usarli questi strumenti.
Sì, certo.
No? Ora praticamente lei è rimasto con una settimana di dubbio, perché me l'ha scritto tipo giovedì o venerdì, quello che era, diversi giorni fa, e magari alcuni dubbi se li poteva già togliere prima. Domani,
certo.
se mi scrive, mi deve scrivere un'email però, in cui mi chiede...
Scrivo un'email verso proprio quell'orario, alle 5 o in giornata?
No, prima, perché diciamo il discorso dell'email è che se io non ricevo nessuna richiesta, non apro la seduta Zoom, mi organizzo
Ok.
per fare altre cose.
Ho capito, va bene.
E
Grazie
niente,
mille.
arrivederci.
Scusi professore, io avrei
Ah,
una domanda, ma a questo
sì,
punto
sì.
gliela faccio direttamente domani o perché è una cosa...
Se è una cosa che posso risolvere ora,
No, perché cioè, il mio
sono
dubbio
anche
era,
disponibile domani, ovviamente. Mi dica.
no, il mio dubbio era quando facciamo un design nello spazio, sullo state, quindi un controller sullo state, e quando lo facciamo magari sull'output, cioè qual è la situazione migliore? Diciamo, quando è che dobbiamo scegliere magari se fare un controllo sullo stato o un controllo sull'output?
Allora, diciamo che distinguiamo l'esame dalla realtà. Nell'esame il contesto dovrebbe essere più che chiaro. Se vi do una funzione di trasferimento e vi chiedo per esempio delle specifiche che non sapete, che non siete in grado di risolvere con una reazione dallo stato, no? Tipo astatismo, queste cose qui, non le abbiamo fatte. Sapete che si possono risolvere, ma non sapete come, quindi chiaramente il problema implicitamente con reazione dall'uscita, funzione di trasferimento, astatismo, poli, queste cose così. Di solito, se si può dare una soluzione con reazione dallo stato, scrivo esplicitamente lo stato è misurabile. No? Se leggete lo stato è misurabile, significa, questa è un'informazione importante, che eventualmente se necessario la potete usare nella risoluzione del vostro problema. Nella realtà dipenderà moltissimo dalla disponibilità dei suoi sensori, no? Da cosa vuole fare, eccetera.
Ok, quindi diciamo dipende anche da se mettiamo, cioè, mettiamo i sensori direttamente magari sul sistema oppure sull'output del sistema e quindi...
Allora, attenzione, il sistema, allora, noi in questo corso abbiamo associato l'uscita sono le variabili che lei misura attraverso i sensori.
Sì.
Ok? Quindi se lei mi dice metto il sensore sull'output,
ok.
no?
No, certo, sì, ho
ok.
capito. Sì, ho capito. Grazie mille. Arrivederci.
Altre domande?
Scusi, prof, una domanda più a livello logistico sull'esame.
Sì.
Velocissima, ma diciamo, cioè, nel senso, come sarà strutturato lo scritto? Quanti esercizi, quanto tempo abbiamo?
Non lo so.
Okay.
Diciamo, tipicamente ci sono 5 esercizi, 6 esercizi.
Ok, quindi non c'è una formalità.
Allora, sicuramente lei deve partire dall'idea che avrà poco tempo.
Ok.
No? Quindi le cose le deve sapere ovviamente bene, deve capire se ci sono delle strade, no, più corte. Oggi abbiamo visto un esercizio in cui se sceglieva la strada, diciamo, algoritmica pura, scelgo la base immagine di P,
non finisco
risolvo il problema, ma ci metto più tempo ed è giusto che io venga in qualche modo penalizzato, perché in realtà vi sono stati forniti anche delle considerazioni che dicono no, guardate, si può fare più semplicemente così. Quindi fa parte un po' di tutto.
Ok, ma invece a livello, diciamo, della carta semilogaritmica, cioè comunque ci organizziamo
quella
noi...
sarà, allora, scriverò, diciamo, tutte le indicazioni, si potranno avere a disposizione sulla piattaforma SEB. Aspetti che intanto io blocco la registrazione perché queste sono cose inutili. No, sulla piattaforma su exam.net avrete a disposizione le funzioni elementari, quindi quelle è inutile averle in cartaceo. Se volete fare i diagrammi di Bode sulla carta semilogaritmica, vi tenete, diciamo, vi preparate la carta semilogaritmica. Chi mi ha detto? Mi ha detto un'altra cosa?
No, soltanto questo,
Okay.
insomma, ci dobbiamo organizzare noi, diciamo, per stampare ragazzi.
Solo la carta, solo
Sì,
la
sì,
carta,
certo, certo. Sì, perfetto. Va benissimo, grazie.
Quindi,